Today I will discuss gradient descent as an optimization method. Many of the machine learning methods rely on optimization algorithms to build a model. In fact, one may argue that most of the numerical computing itself builds on optimization. For example, when you just take an innocent function like square root of 3, or when you take the inverse of a matrix, an optimization procedure is followed to give you back an answer that is as close to the mathematically correct value as possible. Optimization can be stated as minimizing a given function f. Maximization of a function can be trivially converted to a minimization problem by seeking to minimize minus f of x. As an example for optimization, let's find the value of x that minimizes this expression. From calculus, we know that the critical points of a function can be found by solving for derivative of x equal to 0. The derivative is the slope of the function. Where the function is decreasing, the slope is downward, and the derivative is negative. Where the function is increasing, the slope is upward and the derivative is positive. If we zoom in, we'll see that the function is flat right in the middle here. The slope is 0 and the derivative is 0. So finding where the derivative is 0 would help us find where the function stops decreasing and starts increasing. In other words, we can identify where the function has a minimum. The derivative of this function is 2x minus 8 and is shown on the same plot here in red. If we set the derivative to 0, 2x minus 8 equals 0 and solve for it, we'll find that where x equals 4, the derivative is 0 and the function is at a minimum because it is flat right there. Note that the function may be flat due to other reasons as well, such as at a maxima or at a saddle point. So after we find the critical points where the derivative is 0, we would need to double check whether it is because a minima or not. The problem with calculus solution is that sometimes the mathematical answer is not easy or possible to calculate. Let's look at this example. To find the minimum of this function, we can set the derivative equals to 0 and solve for it, but we cannot really pull out a value of x using our knowledge of math. Or at least, I personally do not know how to solve this problem. All I can do is find an approximate answer. If I plot these functions, I can visualize where the derivative becomes 0, somewhere around x equals minus 1. I can zoom into the plot a little more and see that it is around x equals minus 1.1, but that is still an approximation. It is important to note that when you draw a plot, you are merely showing the values of the function for some sample points. The fact that your computer draws a line between those points does not mean that the function has values along that line. You can imagine cases where the function can go just crazy in between those 2 points, and you would not know it from your plot. To remove the illusion that the plot gives us, let's remove the lines and focus on the points we used to create the plot. Here we see that for a point with x equals minus 1.1, the derivative has a value that is close to 0, but not exactly 0. Let's zoom in a little more. We could try out a more resolved set of x values and hope we may get lucky that for some value of x we can land exactly on 0. But we are not guaranteed to do so. Let's try to develop a strategy that can more systematically explore the values of x such that we can gradually improve our answer and get closer and closer to the correct value. If we calculate the derivative for a value of x and it is positive or slightly positive, we know the function is on the upward trajectory at that point. It's trending up. The minimum value should therefore be on the left of this point. We can move left, say to minus 1.12, and recalculate the derivative. We would find out that the derivative is a negative value, which means that the function is on a downward trajectory at that point, so we need to keep going to the right to get a smaller value of the function. We can repeat this process, deciding whether we should move right a little bit or we should move left a little bit, until we are sufficiently close to a derivative value of 0. We may not get to derivative equal to exactly 0, but we may get to, say, a derivative of 0.00001. For this example, when I followed this process many steps, I got to this value of x. And even that is an approximation. It is not an exact answer. The derivative at that point is fairly close to 0. It is this value. What we just did was to invent a method called gradient descent. What we did not discuss was by how much do we move to the right or to the left at each step. We know that the step size should be proportional to the value of the derivative. If we are at a point that has a high magnitude of the derivative, we know we need to make big changes and take drastic steps. And when the derivative is small, we know we are close to the answer, so we should take smaller steps. Therefore, the step size should be proportional to the value of the derivative. But we need to add a little more control to our step size and introduce a factor. I will use the symbol eta to represent this step size factor. This factor is also called the learning rate. Let's formalize the process of gradient descent. We would start with an initial guess of our parameter. We would then calculate the derivative at that point. We would then update our parameter by taking a step in the opposite direction of the derivative. If the derivative is positive, we would reduce x. If it is negative, we would increase x. And we would repeat this process over and over until we are happy with the result or until we run out of patience. Let's walk through another example and see the values of x at each iteration of the gradient descent algorithm. This is the function that we will try to minimize. And we will start at an initial guess of x equals 2 and use a learning rate of eta equals 0.5. The derivative of this function is 2 cosine of x minus 2 sine of x plus 1. I have shown here the plots of the function and its derivative for reference. We don't really need to create this plot when we are working on the gradient descent algorithm. I'm just showing it to help you understand the process. We take our initial guess of x equals 2 and find the derivative at that point. I just plugged in 2 into x in this formula and found out that the derivative is equal to minus 2.6. This step is minus eta times the derivative, which gives us minus 5 times minus 2.6, resulting in plus 1.3. This is the step I need to take from where I am now. So I'll add 1.3 to 2 and get 3.3. So 3.3 is my next guess. I'll call it x1. In this first step of the process, I went from x equals 2 to x equals 3.3. For this new value of x, I'll repeat the process. When I plug in x equals 3.3 and find the value of the derivative, I get minus 0.6, which results in a step size of plus 3. That means the function is still decreasing at that point, so I'll need to keep increasing my x. The step value is 0.3, and adding that to my current guess, I get 3.6. 3.6 is going to be my new value of x, which I'll call x2. Repeating this at x equals 3.6, we find the derivative is equal to 0.4, which means the function is now increasing here. So I'll have to go back and decrease x. The step value results in minus 0.2. Adding that to my current guess, I get 3.4. So we start with x equals 2, went to x equals 3.3, we went from there to x equals 3.6, and then came back to x equals 3.4. We can keep repeating this process over and over until we are satisfied. Here I am showing the values of x that we would explore during the gradient descent algorithm. As you can see, the values of x fluctuate around 3.45, and eventually these fluctuations become smaller and smaller and negligible. Here you can see that the difference between the 60th and the 61st iterations is very small. I told you that we would stop the iterations when we are happy with the results. How do we formulate that exactly? We can recognize that we have gotten close to a minima if an iteration doesn't result in a big change. And we can use this to stop the iterations, knowing that we have come close enough to the final answer. We can look at the value of the derivative at each iteration and stop when the derivative becomes a very small number, smaller than a predefined threshold such as 0.001. Or we could stop when the change in the value of the function for consecutive values of x is small. Another option is to stop when the change in x, in other words, the step size, is too small. And as a last resort, we can stop when we run out of patience, which translates to stopping after a fixed number of iterations. We can also use any combinations of these criteria such that we would stop when any of them is satisfied. Another issue that we have to resolve in the gradient descent algorithm is what value do we use for the learning rate? If we use a large learning rate, we would end up taking huge steps at each iteration and causing large back and forths around the minima, overshooting the target at each time and never really getting close to the minima. If we use a small learning rate, we can guarantee that we won't miss the minima, but taking small steps means it will take many more iterations to get there. In other words, it would take a long waiting time before we come up with an answer. The learning rate should therefore be carefully chosen. Some typical values are 0.01 or 0.001. There are some more clever ways of setting the learning rate. A commonly employed idea is to implement an adaptive learning rate either by a predefined schedule or by a set of reactive rules. An example of a predefined schedule could be to start with a large learning rate and then to gradually decrease it over the course of the algorithm. That allows us taking large, risky steps at the beginning and slowing down at later iterations as we supposedly got closer to the minima. An example of using reactive rules is to keep track of the sign of the derivative. If we have been moving in the same direction, we can increase the learning rate, allowing us to get closer to the minima faster. And if the sign of the derivative changes, that would mean we have overshot the minima and need to slow down, so we reduce the learning rate. These are some basic ideas. There are more elaborate methods for automatically setting the learning rate. As I mentioned before, when we reach a point with a derivative of 0, that does not necessarily mean we have reached a minima. We could also be at a plateau. The gradient descent algorithm would get stuck there because the derivative is 0 and consequently the step size delta x is also 0, regardless of what learning rate we choose. One solution to this problem is to introduce a momentum term so that at each iteration we borrow some of the change and speed that we had from the previous iteration using a momentum factor gamma to control the contribution of the momentum to the current step size. Typical values of the momentum factor is between 0.5 and 0.9. Using a momentum is similar to having a ball roll down the hill. If it has picked up some speed, we keep using that speed to get through any flat spots. Perhaps a much more serious problem that we are faced with in the gradient descent is that once we have reached a low point, that low point may just be a local minima, meaning it is the minimum point in that neighborhood, but not necessarily the lowest possible point for that function. We were just unlucky that we started at the wrong initial value. Had we started at a different value, we would have ended up in the actual minima, also called the global minima. One strategy to overcome the local minima problem is to repeat the entire gradient descent algorithm starting with different random initial values, making it more likely that one of those random starting points will lead us to the global minima. This strategy is also known as random restarts. Now that we have learned the basics of gradient descent, let's now talk about how it can be applied to some of the other problems than the ones I described so far. The examples that I demonstrated so far were in one dimension. The function whose minima I was trying to find was a function of just one variable, and we had to adjust just one variable in the gradient descent. In two or higher dimensions, we would make use of the partial derivatives, which is also known as the gradient field. Let's work through an example. Given this function right here, we take its partial derivative with respect to x and its partial derivative with respect to y. Let's use an initial value of x equals 4 and y equals 5 and a learning rate of 0.5 and find out where we should move next. Plugging in x equals 4 and y equals 5 into the partial derivatives, we get the vector 30 and 2. The gradient descent formula is same as before. We take our current location and move in the opposite direction of the gradient. Subtracting 15 and 1 from our current location gives us minus 11 and 4. So the new values of x and y are minus 11 and 4. When you review other tutorials on gradient descent, you may find it explained for a two-dimensional function. So I just wanted to show you how the gradient descent algorithm is typically demonstrated in 2D. If we have a function of two variables, x and y, the value of the function can be visualized in 3D. The height of the surface and also the coloring reflect the value of the function f for any given x and y coordinates. The goal here is to find a location of x and y where the value of the function is minimum. Starting at a random initial position of x and y, we take steps, we walk, if you will, on this surface on a path that takes us to a minima. The concepts that I described in one dimension, such as adaptive learning, local versus global minima, are still applicable in two dimensions or in higher dimensions as well. Sometimes, rather than minimizing the function fx, f, we may want to have it replicate another function g as closely as possible. This is typically the case in machine learning methods, where f represents the machine learning model's output and g represents the correct outputs that we wish the machine learning model would learn to replicate. Note that in this notation, we try to optimize a set of parameters theta, not the variable x. The variable x represents the samples that we use to train the machine learning model. The parameter theta represents the machine learning model's internal parameters that we would like to adjust as we train it on the samples. We can convert this problem to a minimization problem by defining an error or cost function that captures the difference between f and g. A common error function is the squared difference function. Taking the square allows us to take the derivative more easily. We could have taken the absolute value between f and g, but then the derivative of the resulting function would not be easy to deal with. The smallest value that this squared difference can have is 0. Minimizing this error function would therefore mean we are making f and g as close to each other as possible. Having defined this error function, we can then apply the gradient descent minimization as we have described before. In some other problems, we may not have a mathematical formula for the derivative. This is especially the case for data-driven applications where the value of the function depends on whatever samples we have. One solution is to estimate the derivative by calculating the slope within a small increment from x. Another solution is to take a small step forward and take a small step backward, and whichever one is smaller, move in that direction. Before I conclude, I would like to review some of the related terms and methods you may encounter. The function that we try to minimize is sometimes called the objective or the cost, error, loss, or energy function. All of these functions essentially mean the same thing as far as the gradient descent algorithm is concerned. When we are working with a maximization problem, we may say we are using steepest ascent or hill climbing method, which in essence are the same methods as gradient descent, except rather than moving in the opposite direction of the gradient, we move in the same direction of the gradient. An alternative is to negate the objective function and convert the maximization problem into a minimization one. Another name for the gradient descent algorithm is line search, because we keep moving along a single direction in each step. Gradient descent is a first-order method because it uses the first derivative of the function. Gradient descent is known to have poor convergence. It takes too many iterations to converge compared to some of the alternative methods. A more commonly employed method that converges faster is Newton's method. Newton's method is also known as the conjugate gradient method. It uses the second-order derivatives to calculate a more direct route to the target. The increased complexity in the calculation or estimation of the second derivative is usually worth the time it saves in reducing the number of steps to convergence. In conclusion, gradient descent is an easy-to-implement algorithm. It is known to have slow convergence compared to other methods. The choice and automatic adjustment of learning rate is important to ensure convergence can be achieved faster. Local minima can be a problem, just as it is with any other optimization method. When you need to implement your own optimization method, gradient descent is a good starting point. When you use existing libraries for optimization, their optimization procedures typically use more advanced strategies such as the Newton's method.